In this lecture, we're going to build off what we've learned about stoichiometry and apply it to problems where we have more information about our reactants. And these are going to be limiting reactant problems. And so the concept of this is really based on having a recipe, but having more of one of our starting materials than we need. So a great example is sandwiches, and there's others out there that do the same thing with hot dogs or pizza or any recipe you can imagine. So the recipe for making a sandwich is 2 slices of bread and 1 slice of cheese will give you 1 sandwich. So if we are starting with 2 slices of cheese and 6 slices of bread, if we were going to make sandwiches, we would only be able to make 2 sandwiches in the end, because the 2 slices of cheese that we have limit the amount of the sandwich product we can make. It also means that we're going to have 2 pieces of bread left over. We can almost think of this as before we start, the change we expect to happen, and after. And I'm going to show you one way to do limiting reactant problems, but if you're curious, you can also look up the BCA method as well, which is similar but a slightly different kind of strategy. But I think this highlights the problem very well, that when you're combining reactants in a chemical equation, especially when you're weighing out things on kind of this macroscopic level, but we're looking at a microscopic reaction, we'll usually have some of one of our reactants left over that have run out of the other component, in this case the cheese, and so can't form products. So if we want to predict the number of sandwiches, we cannot predict those based on the bread. If we predict it based on the bread, we would predict that we would make 3 sandwiches, right? If we predict it based on the cheese, we predict that we'll make 2 sandwiches. And in fact, we make 2. And so here, the cheese is what we would call a limiting reactant. It determines the amount of product that forms. So this means we need to be able to predict based on the limiting reactant, and we'll need to identify that limiting reactant in our problems. So let's walk through an example of this to show how it's done, or how I approach them. So here we're looking at propane forming carbon dioxide and water in a combustion reaction again. And we did a stoichiometry problem like this before. In this case, though, we're given 2 pieces of information rather than 1. We're told that we have 2 grams of propane and we have 2 grams of oxygen that are combined. And we want to know how much CO2 will form. So we're curious about the amount of CO2. And we have information about oxygen and about propane. Before, when we approached stoichiometry problems, we usually had just 1 piece of information, and we used that mass to predict the mass of other reactants or products. In this case, we have information about both reactants, and so we need to compare and identify our limiting reactant, which I tend to abbreviate LR, to be able to predict the products. Once we know what the limiting reactant is, then we can actually predict the amount of product that forms. So one way to approach this is as 2 stoichiometry problems. And this works well if you're the type of person who really likes having one set method of approaching multiple different types of problems. So if you saw this type of problem, the red flag here would be that you had 2 pieces of information about your reactants and you were being asked to convert into another product. So the way I would approach this is to, as always, 1, balance my equation, which is already done, and then 2, build my conversion factors. And this time I'm going to do it with the intention of doing 2 stoichiometry problems. So I'm going to need to know the conversion that takes me from oxygen to carbon dioxide and propane to carbon dioxide. So I'll need a mole ratio that is the amount of oxygen to carbon dioxide. So I'm taking that coefficient of 5 in front of oxygen. So 2 moles of O2 will be equal to that coefficient 3. So 3 moles of carbon dioxide. And I'm also going to need the 1 mole of propane would be equal to 3 moles of carbon dioxide as well. I'm also going to need molar masses for this, and I'll need 3, 1 for each of the reactants and 1 for carbon dioxide. So the molar mass of propane, I will calculate from the periodic table as we've done before, C3H8. That's going to be equal to 44.097 grams per mole. The molar mass of my oxygen is 31.998 grams per mole, again calculated from the periodic table. And the molar mass of my carbon dioxide is 44.01 grams per mole. So with these conversion factors, I can now approach this problem. And I'm going to do this in 2 ways. First, I'm going to assume that all of my propane reacts, and therefore it is the limiting reactant. And then I'm going to do this problem again, where I assume that all oxygen reacts, and therefore oxygen would be the limiting reactant. And I'm going to predict the amount of carbon dioxide, and I am going to then compare. So my starting point for this first one is 2.0 grams of propane. And I'm going to follow my steps for solving stoichiometry problems. I am going to multiply by the molar, or divide by the molar mass of this propane. Then I'm going to do a mole to mole conversion to get into units of carbon dioxide. And then I'm going to convert into the mass of my carbon dioxide. So that's going to be the molar mass of propane. So my grams cancel out. And the only conversion factor I have is that has grams in it is molar mass. So moles will go on top. And that's 44.097 grams in 1 mole. I'm going to end with the molar mass of CO2 because I want units of grams of CO2. So the only conversion factor that has mass of CO2 in it is that molar mass of carbon dioxide. So I'll put moles on the bottom. And I have grams on top because I want to keep those. I don't want them to cancel out with anything, and I don't want them to be inverses. So that's 44.01 divided by 1 mole. And then to make sure my moles cancel, the moles of CO2 need to be on the top. So they cancel out with moles of propane on the bottom. So it cancels out with the moles of propane on the top of the previous conversion. And coming up here, for every 3 moles of carbon dioxide, 1 mole of propane made it. So now I have my stoichiometry problem all laid out, and I can plug this into my calculator. I'm going to get 5.9 grams of carbon dioxide. All right, and maybe that's how much I produce. The only way I'm going to know is if I calculate how much oxygen is going to be produced, or how much will be produced from oxygen, and compare. So in this case, my starting point is this 2 grams of oxygen, and I'm going to go through 3 conversion factors again to get to the mass of carbon dioxide produced if all oxygen reacts. So this last step, because I want to be in mass of carbon dioxide, is exactly the same. I want to use the molar mass of carbon dioxide to cancel out moles of CO2 and leave me with units of grams. And my first conversion factor, I need to get rid of this grams of oxygen. So I'll put grams of oxygen on the bottom and use the molar mass of oxygen to do that conversion. So then this moles of oxygen here needs to be on the bottom of my middle conversion factor, so it cancels, and moles of CO2 on the top. So that way I can see my moles of CO2 will cancel, these moles of oxygen will cancel, and grams of oxygen will cancel. I'll plug into the numeric values now that I have used my units to develop a strategy. I like using the units to do that because otherwise I find I flip things around a lot. And if I am careful and rely on my units, I can convince myself that plugging this into my calculator will give me a reasonable answer because my units will cancel out appropriately. So there's 31.998 grams in every 1 mole of oxygen. And there's 44.01 grams in every 1 mole of carbon dioxide. And it looks like 5 moles of oxygen will produce 3 moles of carbon dioxide. Now, if I plug this all into my calculator, I get 1.7 grams of carbon dioxide. And here's where I do my comparing. If all of my propane reacts, I'll produce 5.9 grams of carbon dioxide. And if all of my oxygen reacts, I'll produce 1.7 grams of carbon dioxide. So after I have 1.7 grams of carbon dioxide form, I'm completely out of oxygen, which means there's no oxygen left to continue making the remaining carbon dioxide that can form from my propane. That makes my limiting reactant the oxygen, because this one is smaller than the answer I got from propane. So oxygen is my limiting reactant, and I produce 1.7 grams of carbon dioxide. Now, if you like simplifying things a little bit, this will work really well because you always get your answer at the same time too. You know that the answer you'll report will be 1.7 grams. But if you like figuring out what the limiting reactant is first, you can really stop this calculation and compare after you have the number of moles here. So you can always compare the moles of CO2 that are made from the propane or from the oxygen. And here you would see that we would have less moles of oxygen, and then you can finish the calculation by converting moles of CO2 to mass. It's another way to do this approach. And here on the next page, we've typed this out, so that way you can look at this as well. Another kind of strategy that helps some people is whenever you see a stoichiometry problem, the first step you do is just convert everything to moles. And then worry about the rest of the problem solving strategy and focus it as just your conversion to CO2 second. So there are always a couple of ways of kind of formatting how to approach these problems. Again, kind of play around with this with a lot of example problems, because that's the best way to learn a problem-solving strategy that needs to be applied in a specific way each time. Play around with this and develop a pattern that works really well for your brain, and write it out on like a note card, and use that note card as you do these practice problems again and again and again until you don't really need the card anymore. So this is a follow-up example problem from the one we did previously with our stoichiometry lesson, looking at catabolism again. And give it a try before we walk through the solutions, which I'll do in another video. And in this case, we're going to assume we have a limited amount of oxygen. Instead of all the oxygen we need, we're only going to have 2 grams. And so try the stoichiometry problem that comes from that.